I'd like to get the talk started. We'd like to welcome Archan Misra from IBM Research. He is a technical staff member at IBM Research, and he has been working with us on a couple of projects, including the Orbit project, and has worked in wireless LAN, MAC, ad hoc network type of topics. So he is here today to give us a lecture on a slightly different topic today. And I'd like to welcome you and please use it as an informal audience, and we have about an hour for the whole thing. Okay.
Yes. First of all, good afternoon. Thank you very much for having me here again. Quite a few of you are, I see, familiar faces. I was here giving a talk maybe 2-3 weeks back. If you remember, that talk was more sort of mathematical, theoretical, with not as much a protocol flavor. So I just wanted to give sort of the transition, because today's talk is going to be a little bit, some amount of math, but not really hardcore math. It's going to be more about protocols and alternatives and so on. So the title of the talk is Information-Theoretic Location Management Algorithms. Now, probably, immediately what jumps to mind is information theory and location management. Now, they don't kind of tend, obviously, to sit together, because most of location management work is about paging, location updates, more protocols and algorithm work. As I explained this, this is sort of reflects what I do. I'm not going to be doing any new information theory stuff. I'm not proving, any new Shannon bounds or anything. But it's all sort of using coding theory, using ideas from information theory within this context. And I just want to explain what it's going to be. It's going to be an hour's talk. I'll probably take about 55 minutes and then leave it open for questions. And I will skip a lot of slides because, I have to say, not so much in my defense, but honestly, I put these slides together in 36 hours. So very often you'll find symbol mismatches, some animation out in the wrong order. So do excuse all that. So I try to keep that to a minimum. So let me jump into the topic first, quickly. So for those of you with an EC background, which is, I guess, all this room, you know what the fundamental of location management in a cellular environment or in any environment is. You're trying to track a user from a mobile device, and there are two fundamental operations that you can perform. And the two classical operations are the location update or registration, which the mobile tells the system, I'm here at this time, at this instant, I'm here. And the here could be cell ID, it could be geometric coordinates like GPS readings and so on. For establishing, if you look purely at location tracking is enabling you to connect to the device, it seems like what we call symbolic coordinates appears to be more natural, because all you want to tell the system is I am associated with this cell tower, with this base station, and so on. It's not so much, you want to identify yourself relative to the topology of the network and not the absolute geometric topology. So that's the location update, and then you have paging. So, I don't need to belabor this point. You need both, because if you went to one, these are the two extremes of the spectrum. So if you only did location update and no paging, so every time a mobile changes its location, it would have to tell the system, I'm here, I'm here. And given that communication is only sporadic, and that most of the time the mobile is idle, that's a huge drain on mobile resources, on the battery power, on the channel bandwidth, so on. The paging is the converse. If the mobile never told the system where it is, the system could essentially search for it over the entire possible topology of the network. And it's where the system is doing a where are you search. So you need efficient paging algorithms. So where does information theory come in? I mean, a lot of the work in location management looks at efficient algorithms for, predicting location information, for figuring out profiles of movement and so on. But one way to view this as key to location management is uncertainty. What are you really trying to do? You have a mobile, if you think of it as a stochastic process, you're trying to predict a future sample path of this mobile. So if you believe it's like that, then at that point, even the mobile itself is not completely sure of its future location, because if you think of the device, it doesn't know where the user is going with it. So the user even doesn't know where he's going. So the idea is that this talk is going to be about two different things. It's going to be about a framework in which you express this uncertainty mathematically and for arbitrary movement patterns. So we are not going to be tied to a specific movement model. And then, the obvious fallout of that is, all the usual concepts like entropy, mutual information, and they come in. So again, this is still very much in primer mode. So here's how the current present generation PCS systems do location management. they basically form clusters called registration areas, so the smaller hexagons are cells. And then what the mobile does is every time it moves into a registration area, it sends an update. And then for every subsequent movement within that cell, within the registration area, it didn't send an update. But then it sent an update again as it moved into cluster 2. And then it might move around randomly, and then again an update when it enters cluster 3. And this is paging. So the system knows that the mobile, it may have moved here, it didn't report, but the system knows that it's going to be in one of these cells. So it obviously searches in all of them simultaneously. So the current method is, you kind of flood the entire registration area to figure out where the mobile is. Couple of, actually 3 observations. First of all, this management scheme is global. It doesn't exploit, the individual behavioral patterns of each mobile, the movement profiles. It does not learn. And of course, again, these are all sort of classically well-known points. Searching all the cells of a single registration area is very wasteful because you have better mobility profiles that you can construct. So some of the major themes from what the prior art in this is. So there's a global scheme that does not consider MN or app-specific characteristics. And this is becoming actually more important now. In theory it's been talked about for a long time. But for a long while, the wireless cellular infrastructure was all about cell phones. But it's only now that you begin to see that a cellular infrastructure is, like extremely resource, heavy resource devices like laptops, and then, tiny devices like your keychain and RFID devices and so on. Something with very limited power on it. So the spectrum, the diversity of devices connecting to the infrastructure is only now beginning to sort of increase. Now there were lots of event-specific update schemes that exploit specific properties like location, directional preferences, like, you have things like the updates where you specify a velocity and then if you don't change, you don't report, like dead reckoning type schemes. So all of that, or then you have schemes that exploit specific mobility to call ratios, patterns of that. So but in all of those, you have to construct a model. You don't know the model ahead of time. So there's a lot of signaling and learning that happens offline, and the model construction is expensive. Now there are obviously, that's the update side. And then there are better paging schemes that lower resource consumption by essentially searching more likely areas. And there's this classically known result. It's kind of obviously, in some sense, intuitive, that if you can construct a set of residence probabilities that without any constraints on the delay, the best way, the minimum expected cost on your paging delay, well, the minimum expected number of pagings that you will have to do is if you go at them one by one, starting with the most likely cell, then you page the next most likely cell, and so on. So all this is prior work. So one of the questions to ask is that for any mobile, what's the minimum amount of signaling that you need to track the location of that mobile? And the answer to that is the randomness of the MN's movement pattern. And I use the word randomness without quotes. So I'm looking at the mobile's movement as a sample part of a random process. So there's some information contained in that process, and this is what information theory is all about. It's how much information does the next sequence contain. So Shannon's entropy formulation expresses this randomness mathematically. So the more random a source, in other words, the more unpredictable what the next sequence is going to be, the more is its entropy. And fundamentally, you will need more information to actually capture the event or predict the event. So this is the basic idea that the greater the unpredictability, the greater the signaling cost to actually get information about where the mobile is. Just some base mathematics. If there's anybody who doesn't understand, I'll just mention. But okay, so you have entropy defined like that for the random variable, but for a random stationary sequence, you can define it one of two ways, and I use the asymptotic definition of conditional entropy, and it converges to a bound. And so I'm looking at the mobile's movement pattern as a random piecewise stationary sequence. All said and done, let's see where I want to go next. So for a random sequence X, Hx defines the lower bound on the number of information bits needed per symbol to convey the actual realization. Now, of course, again, in classical information theory, we know that this is all asymptotic. You can only realize this through infinite delays and so on. Again, for those of you who don't directly have extensive exposure to communication theory, the basic idea is that in the long run, only those sequences where the number of symbols appears in the probability of occurrence of those symbols, only those sequences will appear likely. I mean, those are the typical set of sequences that happen. So you only need to care about those. But perhaps the most important problem is that with this model, I have a theoretical bound. I'm saying no matter what location management scheme I construct, I will never, if you measure the cost of the updates plus the paging that I do to actually get the mobile's location, I can never beat this entropy bound, because this is a fundamental limit. Now I want to talk about this scheme. Now this is not my invention, but I want to give you this background work because I've been building upon this. So there's the lazy updates management scheme. This was actually, I think, an award-winning paper in Movicom 99. So here the observation is you look at the mobile's movement as a sequence of symbols. And then what you do is you want to convey this information to the system, because the system can actually learn from the sequence of symbols what the patterns are. You want to do pattern prediction, really. So if you treat the mobile's movement as a history of symbols, then you do entropy coding on that sequence. So you don't need to send the whole sequence. You compress it to the minimum. You do a source coding on that sequence to compress it to the minimum that you need to send. One of the interesting questions, in contrast to classical information theories, what's the code book to do when compressing a symbol sequence? Any source coding has to use a code book. Unfortunately, the code book, the optimal code book for each mobile will depend on the statistics of that mobile. It will depend on the relative ratios of ones, zeros, or whatever, the cell IDs. So this we don't know ahead of time. And that's one of the interesting things, that you need an online learning algorithm. That you need an algorithm that starts off and does entropy coding without knowing the code book ahead of time, that constructs the code book dynamically. And so this is a completely causal algorithm. And there's this well-known class of algorithms, the Lempel-Lib ones, which is which have this online learning property. So here's the lazy update algorithm. So let's think of this as a sequence of cells. Now these are all cells. So this is actually the mobile's movement pattern. What lazy update does is first uses the LZ compression technique. It breaks this up into non-prefix segments. So A, J, L, O. So the idea is that in any segment, if you leave out the last bit, you have seen the previous sequence and one of the earlier segments. So L, you have two L's there, but you haven't seen LO. So you break it up into sort of non-overlapping segments, and then you code the mean sequence as the ith entry in your code book. So for example, and this is what the mobile node is doing, just to give you a flavor of the algorithm. So the mobile node is saying that my first entry in the code book is A, second entry is J, third entry is L, fourth is LO, and so on. However, what does it send the system? Because it's doing compression. What it sends the system is saying, here's an entry, and this is the first entry because it's ordered, and that's A. The second entry is J, the third entry is L. Now the fourth entry is interesting. The fourth entry is actually a pattern LO. But what it only needs to send the decoder, the system, is that this is actually going to be your third entry plus an O. Because that's the property of the system, that the new segment is basically, except for the last one, the remaining segment is actually a prefix, an exact prefix of some other code book entry that you've sent before. So what you're having to send, therefore, if you think about the size of the code book, you're sending a logarithmic in the number of size of the code book plus one extra bit or one extra symbol to send the new update. And over time, what is happening is you're concatenating larger and larger sequences because you've seen all these sequences before. And this is a property that asymptotically, the number of bits required asymptotically per symbol that's generated reaches HX times N. What does the system do? So I gave you the update side of the mobile. What does the paging side do? What the paging side does is it basically constructs a trie. What it does for every sequence coming in, so I give you an example of, you got a new update, it decoded it, realized it's JAA. This is what the system, each of those is a cell ID. So then it constructs all the suffixes of JAA, which is J, A, and A, and it increments all the prefixes, increments a counter for these. So this is what it's doing, is basically it's building higher order context. So in the long run, one of the things is you can model a system as some n powder Markov process, where if the larger you make n, the more context, the more sort of history you're building into the system. But with this online learning algorithm, you can asymptotically outperform any finite order Markov process, because you are learning more and more as time goes on, and you're building this tribe. Again, I want to keep this short because, as I said, this is not the core idea of the paper, but of this talk. But you should at least understand, what we are building upon. So the paging algorithm of lazy update is, you basically get a set of sequences and you have got nothing back from the system, nothing back from the mobile. So then the system says, where is the mobile? One thing that the system knows is that whatever the movement that the mobile has done since its last update, that must already have been seen before. Because that's the reason that the mobile has not sent an update. Otherwise it would generate a new update. So all patterns that are currently in the trie that have, it's actually a suffix of the last updated phrase as a prefix can be considered. So let me give you like a more specific example. So let's say this is the update sequence. I have got this in an entropy coded format, and after JLO I don't get anything more. So then you ask the question, where could the mobile be? The mobile could be in any of the symbols that have appeared before, but they have different probabilities. The first thing you do is you look at LO. You say, have I seen any pattern which starts with LO and continues with something else? Because if I've seen that before, it's likely that that's the pattern that this mobile is doing. Similarly, it says, have I seen any pattern which is starting with O? Because that's the first order Markov context. And then there's the zeroth order context. Actually, I look at all the possible patterns in the trie. And then, using like this prediction by partial match, it builds up the conditional probability. Again, I'm skipping a lot of the sort of detailed mathematics to get to the point of the talk. So here are some observations in the existing world. First of all, the most important point, this is a purely MN specific scheme. So all MNs that have a similar movement pattern have identical So if your movement pattern is the same, your update pattern, your paging algorithm will be the same. However, what that means is that if the MNs, if there are two MNs, one is a cell phone, one is a laptop, both have the same movement pattern, they will have the same updates and the same paging, which is not what we want. We want the system to have some flexibility to trade off between the paging and update costs, depending on the class of devices that you're catering to. And also, I'll come to this point about multisystem movement, which is really the heart of the talk today. The first, and this is where I get into work that I've been doing, let me give you how you can trade off between paging and location update cost in a sort of asymptotically optimal manner. So the goal is to provide a framework and an algorithm that trades off between paging and update cost. Also, and again, I can't say this enough, given that we're doing this work within IBM, one of the things is, at least to our managers, we have to make the point that this is at least plausibly implementable with current architectures. So it's not a major change, a radical shift in architecture. So we have to make the case that it's sort of incremental advancement over current architectures. So I do want to use the array-based PCS infrastructure. The basic analog of fundamental rate-distortion theory. So what we were trying to do so far was we were trying to capture the exact sequence of the mobile's movements. And to do that, you can never use cost lower than the entropy bound of the mobile. However, what rate distortion theory says is, if you want to update at a lower rate, you have to tolerate some amount of distortion in the information you can send. It's basically a lossy system at this point. So what is going to happen at the outcome of this is the system and the MN will have different views on the movement pattern. The mobile node knows the real movement pattern. It knows exactly which cell it visited. But what it's sending is not the exact pattern. It's going to be some approximation of this pattern. Let me skip this. Okay, so this is the definition of rate distortion. So I have this very simple idea that we take the registration areas, and I believe these are 4 registration areas. Let me see if there's animation. Some kind. So what I do is I quantize the cell-based movement of the mobile nodes to an array-based one. So what I'm doing basically, if you look at it from information theory, I'm doing rate distortion by essentially doing quantization followed by source coding, just to give you the basic idea. So cell X, so if there is a cell A, you replace it by Q of X, which is the quantizer, which is the big A. So the update that you send is going to be the big A. So you ask, what's the big difference between this PCS infrastructure that I'm proposing and what we have now? One of the differences is in the current infrastructure, every time you make a transition from here to here, you send an update. In my system, you won't send that update, but that's something that you'll be entropy coding. So there are two proposed techniques, and I just want to give you a flavor of both of those, and there are permutations of the same name. The first one is quantization. Okay, I guess the only point to make is I'll give you the differences between the two update strategies. The paging strategy will remain the same for both of these variants. So let's get to the first LazyRa strategy. This is the same old sequence of cells. What I do is, for every cell, I replace it with the registration area that it is in now. So what you get is the quantized version of the same sequence, but at the symbol output rate is the same. So you get the capital A, P, P, so on, and all of these are with registration area. You now take this sequence, and this is the one that you do entropy coding using LazyRa. So then you code A, P, 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 sequences that you haven't seen before, and then things proceed just as before. And what you send as an update to the system is your first codebook is registration area A, the second one is registration area codebook entry 1 followed by A, and so on. So if you look at it, these two appear to be very identical, except the one is a quantized version of the other. Now, there's an entropy bound of this sequence Y. It's obvious, given all the earlier talk that I told you about, that the remaining encoding will asymptotically arrive at the entropy of this sequence Y. So the first property is Hy is less than Hx. And that's kind of intuitive because Hy given x, given the mapping from a cell to an array is deterministic. There is uncertainty in the mapping from an array to a cell. So naturally, the entropy of this encoded sequence is lower. And now I'm just giving you some results again from classical information theory. Now, in general, you cannot reach the rate distortion bound by just doing a scalar quantization followed by entropy coding. You need, vector quantization to do it. I would love to do that, except that I can't think of a practical way to do this. In that, we want to keep the system simple. However, if you cascade a scalar quantizer with a lossless entropy coder, then there are results that say you can get very close to it. I just want to point out, you get to about, this is a result I forget from Gallagher or Gray or someone, from 0.255 bits per symbol. Now this seems low. However, the truth could be that the rate distortion bound itself is only say 0.2 bits per symbol. So then 0.455 bits per symbol is like 100% increase over that. So it depends on the predictability in the original pattern. So one of the points that I want to make is I never explicitly said what's the distortion metric that I use, and that's one of the things that I haven't been able to come up with, because there are classical distortion metrics like the weighted least squares, or some like for speech there is more like perceptual metrics of distortion and so on. However, for this process, the only distortion metric that matters is how much increase in the paging cost is going to come out of this. And that's not mathematically encodable. Because what you're saying is, if I'm sending less information, how much is my average paging cost going to increase by? And that should really be the distortion measure. However, there's something that we know, that the distortion...
That's the only cost, is it?
Sorry?
I mean, aren't there some other costs associated with, like, the fact that if the system knows the person much well, it's not just that they maybe want the patient, but maybe they want to know some location-based services that will be less accurate, right? I mean, it seems like it's more than just the paging cost.
Yes, I guess what I was trying to say was that for the location management application, which is just trying to see where the mobile can be connected via which base station, this would be the only cost. But in general, I mean, that comes to sort of this, when I was talking with you about this general notion of location tracking, you have to have the arbitrary cost. I mean, if you specify that, if I get information accurate to 50 meters, it's fine. More than 50 meters, there's a cost that I pay.
Can I ask a question?
Yes.
If you don't do a location update, your new algorithm, and how did you get a sequence?
Okay. So I'm doing a location update. See, the difference is, this is the real movement of the mobile.
Okay, so how,
right.
how is ABC related to that? Is that every update of the ABC?
No, yeah. So these ABC are the cells that the mobile is visiting. It's a movement-based update.
But so every cell it visits the network node about the mobile cell.
No, this is all at the mobile side. The mobile knows what cell it is attaching to, right? So that's this cell ID, and it sends this information to the system via this encoding. Okay, I think now there's one sort of refinement we could do on it, but the refinement word you have to look at it with a little pinch of salt. Is okay, we go back to the same sequence again. Just in case it wasn't clear, it's the mobile that is making these movements and is deciding when should I send an update to the system. So what it does is, it first, because it gets the beacon saying you're in this registration area, so on. So it again creates the sequence of registration areas. One of the things you can do is you can cut out the self loops, because it seems obvious in the system, because a registration is a collection of contiguous cells. As you go from, see, if A, B, C, Q, P are in the same registration area, you'll see A several times. It just seems a natural property of the system. So why not remove the run length information of this coding and compress the sequence into something which looks like APZ8. So you've just cut down on that. And then the rest follows. You encode this is what you send to the system.
But doesn't the mental div essentially do a run length encoding effectively?
Yeah, asymptotically it does. If you see the same pattern, I mean, you're basically doing
a long dictionary string of a lot of A's in a row, right?
Which would be one entry in the code book. So you just you send.
So why bother with doing another run length thing?
That's precisely. That's why I said you have to take this with a pinch of salt. That it's an obvious improvement. Asymptotically, it will not result in any improvement with an infinite buffer size, with an infinite codebook size. But if you have a finite codebook and a finite memory, then this will result in an improvement, and I'll show you that. So the paging side of things is the same, except that what you do is you're basically computing the probability of, because your symbols are now registration areas, so you do the whole process and you compute the probabilities of the mobile residing in registration areas rather than mobile residing in individual cells. Now, at that point, because we've lost all information about which cells the mobile visited within that registration area, we use the pop-out. We just say it might have visited all of them uniformly. So we divide that probability among all the cells uniformly in that registration area. So finally, what we do is we go back to the old algorithm that for efficient paging, you order all these cells in the decreasing order of residency probabilities, and then you page cell by cell by cell. So the paging side doesn't change too much. Okay, some mandatory simulation results. One
question. But if the mobile didn't send the update information, the sequence very long time, but your paging domain come in, how the network decide where to start from?
Yeah. Okay. So that's what you do is and that's what is essentially happening in Lempel-Ziv is that as the system keeps on running, the time between updates keeps on increasing and increasing and increasing because you're collecting longer and longer strings. However, the point is that the trie is accumulating context information. So although you haven't updated for the last 50 movements, the fact that you haven't updated means the fifth string of 50 is something that you have already seen before, right? So then what the system is doing is it's basically starting with the prefixes of the last sequence that you updated and seeing which are the plausible continuation of those sequences. Alright, I don't want to say too much about this is not an NS2 simulation. That's probably what I want to say. But it's a homegrown simulator, so that might mean that it's even more flawed than NS2, but who knows. But we basically did a simulation over a period of 12 weeks with 250 cells, and we essentially followed this, the predictable user model. I mean, you had office location and so on. You followed a path every day, but then you took, slightly different routes, and you had different patterns between weekdays and weekends. So one of the things that, before I give you the results, you have to realize is the whole reason we're doing this is because we believe there's some amount of predictability in a user's movement. If it was purely a zero-order random process, then why bother about coding? I mean, there's There's nothing you can do. You should just have to sample them. We have 3 different call arrival states, and okay, ignore this for now. When I get to the multi-system, because it's the same simulation environment, I'll explain why this is important. And the 3 states were sort of different Poisson rates, they're Markov modulated. So here's what the update rates look like. So over the 3-month period, so what we have, this top line is if you did the current PCS architecture, where you group cells into, I think, 5, each registration area was 5 cells. Now, it's not surprising that Lazy Update, which was the original work done in Movicom 99, does much better than that. I mean, clearly, that we already know entropy coding will result in better things. One of the things you see in the lossy update of LazyRa, which is a system where you don't eliminate the self loops, that gives you again, I mean, given that this is on an asymptotic scale, is a logarithmic scale, gives you about a 25-30% reduction. Because really what you're doing is you're trading off location update accuracy at the cost of greater paging cost, and I'll come to that. And RA Lazy does even better. And this gets back to the point that you were making, that asymptotically, if we could run this with infinite memory, they would converge at one point. But they don't converge for realistic systems where you have to flush the memory from time to time and build context. Now, I said, it looks good, right? You pay the lower location update cost, but obviously there is a cost to pay, and that's in the paging. Now, clearly, this is the regular, PCS paging, and here is the lazy update paging, where you spend the actual sequence of the mobile, and that obviously outperforms both of the other sequences, because that's the whole rate distortion theory. Because you had distortion in the information you sent, the paging approach became less efficient. So the paging cost goes up. But you can see that the increase in the number of paging messages is not that significantly high. However,
so where's the x-axis being labeled days?
Oh, that's the number of days over which the simulation was running. So what we are doing is we are counting the number of pagings that have to happen, because you're having calls arrive that per day, how many paging messages
so,
you generate.
So the call that's done memory was kind of like Poisson?
Yeah, the calls were Markov modulated Poisson, different Poisson rates for weekdays, weekday evenings, and holidays, Sundays.
And so somehow, like, what happened at day 22 was like that thing. So something happened around day 5.
Day 7.
Oh.
Day 7. As you went to the weekend, and suddenly it pays off to the 9.
That's a good question.
It should be weekend, right? Because like
so the movement pattern of the mobile changed dramatically.
And
which meant that the learning algorithm wasn't, it was using wrong statistics, and it had to learn that. So that would explain this, but I'm not sure what happened at day 21.
Well, it's not 21, it's 24, right? Which is 3 weeks. Why would 3 weeks?
So,
yeah.
Did you apply this prediction differently depending on each, Sunday, Monday, or?
No. I mean, that happens automatically because you're having different movement patterns on different days. So just based on the movement pattern, we can get the same information. I mean, we don't need.
Something out the tail that it sort of settles down to.
Yeah, because you're repeating the pattern. You're not generating new movement patterns.
And so it just simply is writing in the dictionary. And so when you run one of these simulations, you run an 85-day trace and you run it 100 times.
Right. It was run, I think, 50 times or so, not 100. So, yeah, that's.
But eventually, every mobile has different pattern, right? So over long time, it doesn't mean that the new mobile will apply to the same pattern as the old mobile.
No, so this was run like completely fresh with the same statistics, but the individual sample paths of each run are different. But I guess maybe I didn't understand your question.
Yeah, because based on what every day you're running on the days that it could be a different mobile coming in. It's not the same.
No, this is for the same mobile. I mean, this system is per MN.
Okay.
So we are just tracking for each individual mobile. So if you had a different mobile with a different statistic, the graph would be entirely different.
Yeah, Archan, I have a question.
Yeah.
So, theoretically and conceptually, this is very nice, right? Sort of using ideas from entropy and rate-distortion to sort of do this kind of stuff. But as a practical matter is, when you talk about, say, number of pages per day, what does it mean to say if you reduce it from 12 to 10, or is it really a big deal?
No, it's not.
Okay.
But my practical contention in this particular thing is that I think what the system is doing, it's allowing you to play with the size of the registration area as a parameter. So reducing from 100, or about 90 to say 50 updates per day could be a significant factor for a mobile device.
No, I see the jump from day to day. I'm saying across these three things,
No.
they're all from within 0 to 10. No?
Yeah. So sorry, this is from so from say 10 to 5.
Right.
That could be significant because the point is you're essentially halving the signaling load that you generate. But probably the more important thing is that you can play with the size B now, and you have this sort of optimal framework to say that if you want to drive this lower, you can drive it arbitrarily lower and increase the paging cost, of course. So you're leaving it as a flexibility in the system to say that these mobiles are say running out of battery or they're low on energy, so they need much larger registration areas. So somehow lower the signaling cost on the system. And where this will come into importance is when I talk about the multi-system cellular network. So I'll come back to your question in a minute. So here's the sum of the two costs, and this is the paging and the update. And I think the clear lesson is when you sum of the two costs, which is really the information needed to capture the accuracy of track the mobiles. In the sum, LazyRa and RL-Lazy will obviously do worse than Lazy update because it's a rate distortion. I mean, you're going to pay higher total cost because Lazy update is sort of the optimal signaling algorithm. So my claim is that this framework was only allowing you to do a trade-off. But you would do worse in the total sum, but you basically say let the network take some of the load. I'll reduce the load on the mobile. Okay, so now comes to like what I think was sort of the core of this talk. I mean, it's taken like half an hour, but that's okay. So because all this is a primer. So what I'm talking about the location system in sort of this integrated, the favorite buzzword is 4G network. So what are these networks? So I believe that fundamentally 4G is about having multiple cellular systems. Each of these possibly with different access technologies or even on the same access technology, different providers. And each of these cellular networks have their own topologies, their cell size, etc. And the obvious example, I have my doubt about satellite PCS, but I'll, at least in principle, you have the cellular packet network, you have the wireless LAN and the Bluetooth and so on. And one of the things that hasn't been studied enough in literature is the notion of arbitrary overlap between the cells of different systems and how you do location management across those.
So you use the word cellular to mean the coverage area of a radio, sort of.
Yeah,
an access point.
Or it could be even frequency reuse. It's the range within which you connect to one base station.
Right.
Yeah.
Because, like, for instance, if you said, I think, like, around this room, a collection of wireless and hotspots, right? Like, as a matter of terminology, we wouldn't say that's cellular.
Right.
So, like, in the sense that we use, I think most of the people here use cellular to mean systems that provide, that whose goal is to provide air coverage.
Yeah.
Right.
So
I know what you mean, but it's just
yeah. What I do mean though is that the hotspot, each individual hotspot itself, if you think of that as your world, that could have a cellular structure. Because you have base stations operating on different frequencies and you hop across them, which is not inconceivable. But the hotspots themselves are disconnected islands.
Yeah. Okay.
Right. So the next contention is now the mobile devices have multiple radio interfaces. Now this is something that's coming up. You already see that quite a bit. So for example, you have GPRS and wireless LAN or GPRS and Bluetooth on the same phone. But perhaps the important assumption that I'm making here is you're getting to an interesting paradigm where you could possibly be using these multiple interfaces simultaneously. So you could be doing your voice, voice over cellular and data over a wireless LAN hotspot and so on. But the point is that all these interfaces are active at the same time and you could be using them simultaneously. So, I mean, I did this in 2 days, so excuse. Yeah. Yeah. But you see all these charts. Basically, it's an overlay of arbitrary cellular networks and arranged in some hierarchy. So in this particular environment, what are some of the challenges? What are some of the new challenges? So I think first of all is when to update. Okay, so let me take a step back. I believe that you can do much better by, instead of having each system operate its location management tracking independently, by trying to coordinate the location tracking activities of different subsystems. So have an integrated mobility management framework. However, having said that, there's going to be one big constraint, is that different subsystems, if they're operated by different providers, they're not going to cede, administrative control of their subsystem. They're not going to be exposing their topology databases and so on. So we need to keep those in mind, but I'll get to that. So some of the fundamental questions are when to update. So the cell sizes in different subsystems, I use the word subsystem to refer to a cellular network. They're very different. The wireless LAN has a much smaller radius than a 3G cell. So where to update? Now, multiple interfaces can connect to multiple subsystems at the same time. There the question is, where do we send an update? Suppose we decide that, I need to update my location. Do I send it to all of these subsystems? Do I send it to only one? Which one? How do we page a mobile? I'll answer this question. Perhaps again, just to reiterate this point, where I want to distinguish this work from, there's not been a whole lot of work in this area. But there has been work which essentially says that, suppose we know exactly these two different operators. We know that the cells of 5 and 6 of this operator are the same region as the cell 4 of this operator. And we can do sort of better handoff management across these two. Now, I believe that that's a very unrealistic assumption, because again, from a practical perspective, I've found that cellular operators are sort of paranoid about exposing their topology databases, and these change over time, and they don't want to cede control over
Can I
them.
ask a question?
Yes.
How many modems do you connect at the same time? If there's one modem and you connect to one network, so you have a radio interface, right? Radio interface, you assume if you connect to more than one, each one associated with one network. Or you have one modem connect to multiple networks.
No, so one modem connects to one, but you have multiple transceivers on the system, on the mobile.
So each transceiver associated with one software to send
Right.
data. So in overall, you are going to determine which modem to send to update. Is that what?
Sort of, yeah. Which one to update when?
Yeah, but the way is that when the modem, each modem will associate with the application. So what is the purpose? You have to make a decision for all of them together. Like your voice going to the cell phone and the data goes to them, then what's the purpose? You have two things going to one location update.
So it's not so much the question of two things have to go to the same update, but they should coordinate the system. The whole idea is that you can lower the overall cost on the infrastructure as well as the update cost on the mobile device, rather than having them operate independently. That's the contention. So what this piece of work does not address is the issue of over which network do you provide which application. So the selection of a network at any time. So one of the assumptions I'm making is at some point some global entity or God has decided that you need to complete a call using this subnetwork. At that point, how do we page the mobile in that system? So we sort of extend the same model of location update. So now we, instead of the mobile movement sequence being a sequence of symbols, it becomes a sequence of symbol vectors. Because let's believe there are n subsystems and n networks in the system, in the environment, then each update is basically a tuple of the subsystems. So then you can model the immense location probability as a joint distribution across all these subsystems. So just a little bit of notation. C1 x1 means that the x1 cell of subsystem 1, C2 x2 is the x2 cell of subsystem 2. So this probability basically says that the mobile is simultaneously in this cell of this subsystem and that cell of this subsystem and so on. And you can obviously, given this sequence, you can define an entropy of this vector value sequence. It's a vector value entropy. Now, at this point, again, I'm going through the process of saying, we looked at this problem and said, what are some of the new challenges that we face? So one of the things that we have to worry about is if you're trying to optimize the total cost, in each subsystem you can make the plausible assumption that a paging message costs the same in all cells, and an update message costs the same in all cells. However, across subsystems that's not necessarily true, because in a satellite system the update cost is much higher than in a wireless LAN, or especially in a 3G cellular system. So we introduce some more mathematical notation, and subsystem SI has LUI as the update cost, and these are cost per message and PGI. So at that point, I think that one of the things you have to do is, if you look at the entropy, you have to look at this weighted entropy. Because what you're trying to do is, you're not trying to measure the uncertainty in terms of the number of bits, but with each transmission of each bit, there is a variable cost associated with it. So then the weighted entropy captures the fact. So it captures the fact that you multiply LUI with the fact that if you change your update in the ith subsystem, then the information needed to convey over the ith subsystem is LUI. So it just, it's a natural extension of the entropy model with this weighting. Okay, at this point, what are some of the other advantages of doing this integrated subsystem? So let's look at some of the practical ways you can use. So unlike a single subsystem, if we believe that we collect all of these together into an integrated subsystem, we can now use location management also tied to the mobile's call state or session activity state. One of the interesting things here is that in a single network, you do paging only when a mobile is idle. Otherwise you're tracking the mobile, you know exactly where it is. But in a multiple interface system, the mobile can be idle in one interface and active in another. So then what does it mean for the mobile to be idle? Because if you're trying to page the mobile, because they all potentially have independent activity. So there, one of the observations is knowing that an element is active in one system can help improve location accuracy. So let's say the mobile is active there in SJ, and in subsystem SI you want to page the mobile. And I got the PGJ wrong. So one way to do is subsystem SI independently page the mobile. And that's going to incur the cost of how many cells it pages times the cost of paging per cell. The other way would be you send this indirect registration message. Because the mobile is already attached with subsystem SJ, you tell it, would you please tell the mobile to register with a cell in subsystem SI? Now the obvious advantage is these are unicast messages, because you know exactly where the mobile is. And therefore the multiplicative cost of searching, there's no uncertainty in the system. So one of the first things we do is, we're trying to make this prediction thing work is, we're creating an even longer random vector. So what we do is we associate a binary valued sequence with the call states as well. So let Z bar n be the call vector Z1, Z2. So these are binary values. So it's 0 if SI is idle. If it's idle in radio interface SI, it's 1 if it's active otherwise. So then you create this 2n valued vector sequence yn. I'll give you the example. So with two subsystems, you can have C1 phi. Okay. Let me first introduce phi. One of the things we have to take into account as we talk about the disconnected islands is that unlike the ubiquitous coverage, there are cellular, well, let me not use the word cellular. There are wireless technologies where you're going to be disconnected from them as the norm rather than remaining connected to them. So to capture that, we have this special cell, this I call a virtual cell phi. So phi basically means you're out of range of coverage of that subsystem. So this is the call state vector. Actually, there should be one less 0 here. Again, I apologize for that. But so you concatenate this. What does this mean? This isn't. It's fine. So the total call state is right now the mobile is making a call. It's engaged in communication, but it's resident in the 5th cell of subsystem I. It's outside the range of coverage of subsystem 2, and obviously it's not making a call. And it's also connected with the 4th cell of subsystem 3, but it's idle there. It's not making a call. Now what I'm going to do is I'm going to use the same lazy update algorithm, but I'm going to start doing the compression on this symbol, this vector valued symbol, because now you have a vector valued compression algorithm. One of the assumptions, this is from a more mathematical point, is if you watch the evolution of this sequence, you can make the assumption that yn differs from yn minus 1 in at most one element. And for example, you believe that, let's say there are two subsystems with identical cell coverages and you cross. So you change from both simultaneously. But you can always model that as changing from one to the other, two incremental changes. So we don't lose, the basic evolution model. So then how to update yn? So now we go back, I'm again using the same lazy update approach. We now have this 2n vector valued sequence y. Suppose the sequence is like this, and these are the symbols. Each symbol is of 2n's. Again, I don't really have anything to say. You understand what I'm doing. You're just breaking it up into sequences. You're sending the ith entry, so on.
So who's keeping this state information, and who is acting as what used to be the HLR or something, the DLR? Okay, hold on to. You'll come back.
Do remind me if I don't come back, you'll remind me. But yeah. But one of the questions that I was almost expecting you to ask is, for this codebook to remain in the mobile has to have certain memory requirement, because the mobile is doing a lot of the encoding and processing. So that's, again, remind me if I don't come to that question. Okay, so I already covered this. How do we use the sequence at this HLR, or the system? Now I keep calling it a system. How does this particular location management node within the cellular infrastructure use these updates? So now it still builds that decoder trie, but now the trie is full of vector valued symbols. So you use the same method to essentially get the probability of various vectors. So how do you go from the vectors to the individual cell probability? So here is an example. If you used the exact same algorithm that I described before, you would arrive at this step. You would say this vector has probability 0.3, that vector has probability 0.2, so on and so forth. From that, you can construct the probability, the unconditional or marginal probability of a particular cell in a particular system. So rho 210 is you collect 0.3 plus 0.2 plus 0.15. So that's 0.65, and you divide it, in this case by 0.85, that's what these add up to. But essentially you're normalizing them to get the unconditional probabilities in each cell. And once you get rho 20, rho and rho 21. So in this system, you treat the symbols of a mobile being active in a particular cell and being idle in a cell as two different symbols. You get the probabilities for those separately. And I'll come to why we get these probabilities separately and what we can do with them. So once we get the two together, we can construct, the probability that the mobile is in some state, active or otherwise. So first, here's the intelligent paging strategy. Okay, I won't say anything else at this point. So again, we page the cells in decreasing order of normalized residence probabilities. Now this is a trivial extension because the different cells have different paging costs. So there, if you want to get an optimal sequence, instead of just using the probabilities, you have to weigh them by, you divide by their paging cost, and then you get back the same sequence. You page cells which have higher normalized residence probability before you page cells with lower residence probability. Okay, I think one of the questions that comes is, remember we had no topology information. In general, if I'm trying to page in subsystem SI, it might be better to only page in the subset of other networks that overlap with the current cell of SI. Sorry, do you have a question? But remember, that's one of the constraints of our system. If you had that information, you could do even better. You could use locality and location information. But we're assuming we don't have that, but we'll only infer that.
But do you assume, you mentioned that every system has different coverage area. Is that still the same? Is that
yeah.
True? So the joint information doesn't provide you any other system information too, right? Because of the coverage is this one, cell I, for all the subsystem, might be different for I+1.
Yes. So, but that I modeled as you are changing incrementally. If you change all of them, you can view as changing one by one. But that's more a mathematical detail.
Yeah, but the way is that they don't have overlap, so that when you create discrete space, you look at them and probably the first one you can identify how the overlap area in between all the different systems. then they go to next grid of the space, then you will find out.
But the cells do overlap, though. I mean, the cells are all having arbitrary.
Overlap pattern will be different for every grid, right?
When you say every grid, I'm not.
Like if you got discrete location of that for the location system, so it could be covered by 3 systems, but the 4 system was not there.
Yeah.
Then going to 4, the only small portion of the 4 system will jump into that.
Yeah, that will be a different cell ID in that subsystem. In the 4th system, so that's why we have the notion of 5. So in the first one, you're still covered under cellular system 4, except that you're in cell 5.
Okay.
So
this cell 5 is relative to all the different systems, or just a...
No. In each system, there is a cell 5.
Okay.
So you're just okay. So now I come, I guess, to the question about how could we use this, and at this point it's more a protocol stage. So I'm not getting into do we run this over mobile IP? Do we run this over mobile IPv6? On the protocol stage. So one idea to do this would be that for each mobile you have a centralized location register to which all the subsystems connect. This is sort of the home agent of the mobile node. So all the updates from an MN, they go to a central register which maintains this entire trie, because who's maintaining this trie? So what the responsibility of each subsystem would be that every time the mobile sends an update in the subsystem, it will also say, please forward this to my home agent, and the home agent gets that message and construct that trie. Then in the same architecture, then all the paging has to be controlled by the central register. So each paging message in instruction to each subsystem, again by the home agent, can you please try and see if the mobile is in the jth cell of your subsystem? So one of the things is the central entity. Now this could obviously be distributed for different mobiles, just like home agents. I mean, you can always partition mobiles and assign different home agents to look after different mobiles. So that takes care of the scalability problem. What it doesn't take care of the fact is, this is a central signaling bottleneck. So every subsystem that wants to do paging has to ask it, okay, who do I page next, who do I not page, so on. I'm going to skip this rather extended animation. It's making the point that I made. Now let's take the other extreme view, which is completely decentralized. No subsystem trusts one another. Then each subsystem independently maintains a copy of this trie, because the entire paging strategy is based on the knowledge of this trie. There's nothing else you need to know. So this idea is that the MN will send each lazy update, each update of its location to all the subsystems that it connects to. So clearly there's a significant increase in the update cost. But now, there's no central entity sort of controlling the paging sequence of the mobile. One of the challenges with doing this that we found that when we sort of started building a real implementation of this is to keep the tries in a consistent state. With a lot of subsystems, you are going to be disconnected from them for a long period of time, say 3 days. During that point, there are certain updates that the mobile wants to make, but it cannot make with the subsystem because it's not connected to it. But it has to store those, and when it connects to the subsystem, it has to send them all in a batch to get the state consistent across all the subsystems. Now that, it's like a very bad thing because the mobile's memory requirements kind of explode. So the cost here is, if you believe the HY was the location information, instead of each LUI waiting that, you're now updating each update to all of the subsystems. So it's a sigma of LUI.
If MN is mobile node is disconnected from one of the subsystems, then how does it store, keep track of the location, please?
So I'm assuming that, well, it knows that for that subsystem it's in cell 5, but in other subsystems it's connected, and it's doing the compression on the entire the entire tuple, right? So,
okay. But it cannot track for that particular subsystem.
no, it cannot. Till it comes back and connects, it's basically in 5. So that's the location of the mobile. That it's in cell 5. That's what it will tell the system, that when I was in all these other cells of other subsystems, I was in cell 5 of this subsystem.
Okay.
Okay, let's see what I'm going to skip over this because this is sort of a slight tweak to this, because the previous example of paging that I did what I showed the optimal paging algorithm was you would go cell by cell by cell. So pick the highest cell first, do the second cell first, and so on. But what could happen there is that the first cell could be in subsystem 2, the second cell would be in subsystem 3, and the third cell could be in subsystem 2 again. And I believe that that's going to be sort of an unrealistic thing. What you want to do is you want to collect together all the cells of each subsystem that you want to page and do one paging per subsystem and not any more than that. So if you increase that constraint on the system, then we came up with these two different notions of active paging versus idle paging. So in active paging, what one subsystem would do is ask another subsystem, can you please ask the mobile to register with me, with my subsystem, but do it only if the mobile is already registered and active with you. So don't page the mobile. And if the answer would come back no, it says I'm idle. The mobile is not registered. That's fine. And there's a separate message that says, please page the mobile and ask it. You first page the mobile and ask it to register with me. Now, in many cases, that is still advantageous than you paging directly, because the uncertainty in the other subsystem might be lower than the uncertainty in your subsystem, and the paging cost in that subsystem might also be lower than the paging cost in your subsystem. So, there's an obvious formulation to do this, and I'll skip over this in the interest of time.
I think we should try to wind up in
5 minutes, yeah. Yeah, towards the end. So, okay, so here's more equations. Again, you can see all this in the paper. But so this was the framework. This gives you what the ideal theoretical bound does. But unfortunately, these are problems. So, what's the practical solution to doing it? The practical solution to do is let each subsystem operate quasi-independently. Go back to the old model. So in each subsystem, the MN tracks the movement only in that subsystem. So it's an independent location management system. And then you have the location update cost. The difference is that before a subsystem begins paging a mobile, it goes to the central register and asks, are there any better subsystems as far as you know? The way we do that is, periodically each subsystem sends an update of its estimated cost to page the mobile. So, what is my estimate? If you ask me to page, what will be my average cost in paging? So I send that to the central register. And, we use the threshold-based trigger for reporting new changes. So the algorithm for partial paging works like this. Subsystem SI, which is trying to locate the mobile, first computes its own normalized paging probability, using its equation, using its residence probability, so on. Then it queries the central guy saying, do you know of any other subsystem that said that its normalized paging probability is larger than me? Which is a set. If so, then I will try those subsystems first. Now there's an important point here, which might be lost in all the sort of math. This third model, we have completely taken away the call activity vector, because each subsystem is operating independently. Therefore, by assumption, each subsystem you only generate updates or paging only when the mobile is idle. So you can never report this collective information that I was active in this subsystem and so on. So an open question is, with that additional information, we could have better predictions. But since we don't have that, what will be the increase in the paging cost? So quickly, we did some simulation studies with 3 distinct subsystems. The location update and paging costs. For the paging, the satellite has the highest cost and PCS has the next highest. Whereas for update, because the update power of PCS is lower than the update power of a wireless LAN card, so we reversed it, and the rest. Now you understand the importance of call application. So here's a comparison of the update rates. Now this is the classical system, independent threshold-based movement and broadcast paging across all the systems. But what you see is that the selective update heuristic, the third scheme I presented, has the lowest update cost. And the reason for that is that it's discarding all the additional information about the call state. Whereas the other systems, naturally the decentralized one where you update to all subsystems is a higher cost than the other one, where you update to one subsystem. If you look at the paging, not surprisingly, the thing reverses. Because if you do the heuristic approach, then you're sending less information, and that takes the highest, among these schemes, that takes the highest cost. But the scheme where you send complete information takes the lowest cost. And you add these up, and you get an overage, you assign different costs to the update and paging, and you get these 3 graphs. I think the point to take away from this is I gave you the ideal optimal bound. You can't do better than that. Then I gave you a heuristic with which you see that at least for this simulation, you're going to get about within 10%, 15% of the optimal bound. You're going to be doing worse by 10, 20%, which is not too bad because it's a practical algorithm, and we know that there is a heuristic bound to do. Okay, I'm going to conclude with one thought. One of the things is I said we didn't exploit location information at all. We just paged in the order of probability. However, we can do a better job of paging by simply exploiting the correlation among cell IDs of different systems. Remember, we don't know the topology. However, let's say that the blue one is one subsystem and the green one is another subsystem. If you look at the pattern, it will be obvious to you that when the mobile is in cell A, it's also in cell 1. And so if the mobile is not in cell A, it's also not going to be in cell 1. So there is no point in first paging in cell A, then seeing that it's not there, and then paging in cell 1. But how do we do this in a clean manner? So the answer is this is an interesting extension to the basic paging and decreasing sequence. So you look at the joint distribution and eliminate redundant searches. So what you do is you're basically forming a sequence of cells to page. And the way you form that sequence, now the expected cost, and this is what it differs from earlier work. The expected cost in the sequence is going to be the cost of paging in the ith cell, but the probability is not the marginal probability in that cell. It's the probability that the mobile is in this cell, but it is also simultaneously not in any of the other cells before, because then I would have succeeded there. Now in a single system, this probability boils down to pi, because they are mutually disjoint. However, in a multiple system case, they could occur simultaneously, and that makes a distinct difference. So the optimal paging algorithm, and I put a question mark because we know this does better, but I have not yet been able to prove it's optimal. This is an interesting case, which is you have a sequence. At that point, you pick a next member of the sequence that maximizes the residence probability conditional on the MN not being in the previous cells. So you're picking cells by the decreasing order of conditional probabilities. However,
Okay, go ahead.
and I give the example. However, a rigorous, in most cases, all the cases I tried out, and there are some cases where I can prove that it's optimal, but I'm not yet successful. So the one point to make is that if you use that method, where you're basically exploiting spatial correlation by just looking at the distributions themselves, you can again do about 20% better. All right. So that's the conclusion. We already know that. So let me give a little bit of future work that I want to do in this particular area. One of the things that I'm interested in asking this question is you have the notion of registration area in a single subsystem. You ideally want a registration area that spans multiple subsystems. So cell 2 and 3 of subsystem 1, cell 5 of subsystem 2, and cell 6 of subsystem 3 form a registration area. And the mobile sends an update. So that's a more optimal scheme. But how do you form those? And if you think about it, it basically boils down to sort of forming in this multi-dimensional space the right grouping of cells into, this is a vector quantization problem. But the interesting thing is, again, it's the online nature of things that makes a challenge, because you don't know the code book ahead of time. So I'm thinking of looking at online adaptive VQ. And the other point is we did the individual case. For a practical, if this was ever to be deployed, you're never going to do per individual MN. You're going to be doing for groups of MNs that have similar profiles. So there, how do you derive the optimal system, for that group of cells? What's the rate distortion bound or entropy bound for a group of cells, each of which have, the same statistics but different patterns? Okay. Right. I think I finished in time. But any questions?
Did you look at the error when you select the sequence? When there's an error in the sequence? What's the effect of error on that?
Oh, in this, for the LZ compression algorithms, if you have an error in the sequence, that basically it could be catastrophic because you lose entire symbol sequences, and so your paging might fail. You might not search for the mobile in places where the mobile is.
Okay.
So you have to ensure that the updates you send are error free.
Did you mention how to solve the administrative problems among providers?
Yeah. In my did you say how you solve the administrative problem among providers, among multiple providers? So this scheme, what it does is, you realize that even if providers don't want to expose their location information, there's one guy who actually knows all the cell IDs, and that's the mobile node. Because it's seeing that, cell tower 2 of system 1 and cell tower 3 of system 2, I'm getting beacons from both. So I'm simultaneously associated with both of them. So in my sort of independent scheme, the heuristic scheme, there's a centralized guy, and each subsystem has to agree to periodically send an estimated update cost to this centralized register. And that's the only coordination needed among them. So that's the administration, if you will. They don't need to talk or trust one. I mean, of course, I'm not getting into the notion of trust. I mean, what if you say,
carrier willing to do that?
That I believe that the carrier should have no problems exposing if it believes that it's driving down the overall cost of the system and it's allowing its own. See, there it's the argument is your customers will benefit if you do it because others will do the same for you. So. I'm not yet at the stage where we look at the practical implementation of it. So I don't want to.
Association to standardization.
It's too. I think it's premature for me to even talk about this. The multi-system network has to come up first. But I think the central message is that yes, paging and location management is really an old classical problem of relatively low interest, but for the multi-system,
I'm agreeing.
Now, it's been solved. There are a lot of schemes, but if you believe the multi-system architecture, I think that throws open new problems that have not been solved. So this is not a dead area. That's my belief.
But the new problem could be the 3G and 2G system overlay, and in the problem 3G, that's how they're going to look at the location and how they're going to hold out the 3G form and 2G form.
Yeah, I think what you are talking about is more a protocol issue of,
no, you could. Location of it. There's a real field issue they are talking about now. I have a GSM form, I have a new UMTS form coming in. And this form is still more UMTS form, GSM form. So when the form coming in from the network side, which one is going to run?
Okay.
Here.
Right, so that's a selection of provider selection.
No, it's the same provider.
Okay.
Same system, because same like 18 to 1 on the UMTS and GSM form in the same area. So the incoming call coming in, which route system going to run?
Okay.
They're going to replace location and everything. So this is
well, I shouldn't see that as being a location. That's being more a resource optimization. Which channels have more bandwidth. That's not related to the mobility of the node. They could be with static nodes as well. It's the same problem. That's my contention. That you have fixed 5 nodes which are GSM, 5 nodes which are.
No, the two systems overlap. Mm-hmm. So the way is that you still have a registration on both.
Okay.
Right? And you still paging strategy for both.
Right, which is the independent model.
So that's the same thing as what you were talking about.
Right. Yeah. Okay. Any other questions?
Thank you for attending, but he has an appointment with someone, so I need to get it back.
Okay, thank you very much.